Hi students, now I am going to explain one of the topic in fifth module is shift registers. If we are going to start shift registers, the basic elements which are required to this topic is that sequence circuits like latch and flip-flops. The flip-flops are the basic elements by which we can make the shift registers. So as I explained earlier, as we study this flip-flops, we are going to use those flip-flops in different areas, one of which is shift register. Now let us see that how to start these registers. First of all, what is register? Register is a memory element. And how can we make these registers or memory elements with the help of flip-flops? And flip-flop is a 1-bit memory cell by which we can use for storing the digital data, either 0 or 1. The capacity of one flip-flop is that which can store 1-bit information, either 0 or 1. As we increasing in series, when we connect it together, one flip-flop after another flip-flop, we can make these registers. So to increase the storage capacity in terms of number of bits, we have to use the group of flip-flops connected together. Such group of flip-flop is known as registers. So the registers made with the flip-flops, group of flip-flops. So based on our requirements, we can connect how many number of flip-flops are connected to one another. If you see that n-bit register will consist of n number of flip-flops, and also this register is capable of storing n-bit information. When the n is equal to 4, then it requires 4 flip-flops connected together to store 4-bit information. As start from which can store from even from initial value of 0, 0, 0, 4 zeros, and then final value, the maximum value which can store in that 4-bit register is 4 ones. When we converted into that number into decimal or hexadecimal, when we converted into hexadecimal, that 4 ones represents F. We can store a hexadecimal number F in a 4-bit registers. So more than F, we can't store it in a 4-bit register. So if you want to store n-bit information in our register, we can prepare that n-bit register or n flip-flops. The binary data in a register can be moved within the registers from one flip-flop to other flip-flop. The movement that the transfer of this binary information from one flip-flop to other flip-flop, the data transfer from one flip-flop to other flip-flop towards to the left to right or towards to the right to left. So based on that, we can call it as a register call it as shift register. This momentum of binary information from one flip-flop to other flip-flop will help to prepare from applications. If you want to change the state, if you want to change the data information in our registers from one state to other state, then that it needs to be changed from that one data from one flip-flop to other flip-flop. The registers which allows such data transfer are called as shift registers. And also the bits stored in these shift registers shifted when the application of clock. Without application of clock, so then the data never be shifted, moved towards to the right or towards to the left. Every time the sequential circuits will, most of the time in a synchronous sequential circuits, operated with the application of clocks. Next, we can see that when we see that shift registers, basically there are two types of shift registers to which direction it shifts. A shift register can shift the bits either to the left or to the right. And also a shift register which shift the bit to the left, like a bit to the left, is known as left shift register or shift left register. Similarly, when it shifts the bit to the right, which is known as right left register, uh, right shift register, right shift register, or shift right register. There are four mode of operations of shift registers based on either it is left to right or right to left. Both cases we can see that the mode of operations of shift registers. We can have different kinds of shift registers. Serial input and serial output. We are providing the serial input to the first flip-flop and we are fetching the serially at the last flip-flop output. So as we giving input to the serial and collecting the data in a serial at the last flip-flop, then we can, comes under serial input and serial output. Input given input is serial, fetching in output is also serial. And then the second one is serial input and parallel output. This serial input and parallel output, the input is giving serially, but collecting after getting all the information available at the flip-flops, 10 flip-flops, then it is ready to fetching the output parallel. Parallel input, serial output. We are loading the data in parallel. As we providing the data in parallel, once the data is available, so then we were used to collecting the data in serially at the last flip-flop, whether it is based on the left shift or right shift. Parallel input, parallel output. So given data is parallel and collecting the data is also parallel in this case. And bidirectional shift register. Both direction which will works both direction to shift the data left to right or right to left. And a universal shift register which can perform any shifting, any data, any mode of operation, which can perform the all mode of operations and also both the shifting, left shift and right shift, so that we can call it as universal shift register. Let us say serial input and serial output. The data shifted in or out serially. As I said, we are giving the serial bit. Suppose when we have four bit 4-bit register, whatever the data I am giving, 11110, let us take it is left to right shift. This is the first data need to be fed into the first flip-flop, and then following which second bit, following which third bit, following which fourth bit, serially they are fed into the register. This is the diagram. This is the diagram which we can have the serial input, serial output shift register, and this is the basic fundamental, the main input data input DN is given to this third D3 flip-flop, D2 flip-flop, D1 flip-flop and D0 flip-flop. Third flip-flop, second flip-flop, first flip-flop, flip-flop 0. In each case, clock is connected synchronously to all the flip-flops F3, F2, F1, F0 synchronously. And also it is our wish whether it is working with a positive edge or negative edge. When it is work with negative edge, the clock is whenever from 1 to 0, then the flip flops are enabled, and then the shifting action performed. In this serial input, serial output, we are providing the data, main data input at the D3 flip flop, and the output of D3 flip flop, nothing but O3, is feed to the input of the second. The output of the second is fed to input of the first. The output of first is fed to input of the D0 flip flop. And finally, we can fetch or collect the data serially at the last flip flop output Q0. That is what we can see here. Single bit shifted at a time in either right or left direction under clock control. Initially, in all modes of shift registers, let us consider this case, let all the flip flops be initially in the reset condition, that is, all the outputs Q3, Q2 is equal to Q1 is equal to Q0 is equal to 0. The D input of F3 is connected to, that is, D3 is connected to the serial data input. The output of F3 is connected to the input of the next flip flop, so on and so on, so that we can make the serial in under serial out shift register. This is the block diagram for serial in under serial out shift register. In this case, when the clock signal application is disabled, the output Q3, Q2, Q1, Q0 is equal to 4 zeros. The LSB bit of the number is passed to the data input Dn, that is D3. So when the clock when the clock is applied, immediately the data which is available serially at the D3 input is passed through the D flip flops. First D3, then D2 and D1 and D0. We will apply the clock, and this time the value D3 is 1. The first flip flop, that is F3, is set, and then the word is stored in the register at the first falling edge of the clock. It is our wish whether it is the registers work with the falling edge or rising edge of the clock. Now the stored word is 1000 because this is the left to right shift. Okay, so the data which is available, the marked with the Q3, Q2, Q1, Q0. So this is outputs of data after applying the first clock. So it is serially passing through the data. So whatever the data logic 1 available in the D3 in the first clock, falling negative edge clock, that data is available in the output of the first Q3 output. Remaining all are the zeros. Remaining outputs are zeros. Likewise, this number, next time this number is moved to the input of the second flip flop, so that it will pass to the output of second flip flop. So we can see that the output of the first clock is, because I am giving data 1 here in the clock at the time of clock, so that after applying the clock, the data is, this 1 is passed to the Q3, and whatever the D2 0 is, initially we can have all the inputs are zeros. So D2 is 0, the D2 0 is passed to output, D1 is 0, 0 pass, and D0 is 0, that 0 is passed to Q0, so that the output after applying the first clock is 1 0 0 0. This is what output we can see in this figure. Apply the next bit D0, next bit to D0. So D1, D input is equal to, not D0, D input. D input is equal to 1 again. As soon as the next negative edge of the clock hits are applied, flip-flop 2 will set and the stored stored word change to Q3, Q2, Q1, Q0 is equal to 1100 because already we can have the output of Q3 is 1 in the previous 1000. This Q3 output is fit to the input of second flip-flop so that at the second clock we'll get this one. At the same time, we are providing D input is 1. That D in 1 is come to this D. The remaining will be 0. That is what we can see here. So second, at the time of second clock, we can be providing the D3 input is 1, that is passed to Q3. Same time, we can have the Q3 available one, that one is passed to Q2. Remaining bits, two bits are 0, 0. As soon as the third negative edge clock hits, FF1 will be set and output will be modified and that's 111 zeros. Remember that each time I am feeding the logic 1 3 times. 111 it shows that Q3 output 1, Q2 output 1, Q1 output 1, Q0 is 0. And finally, in the fourth negative edge clock arriving, the stored word in the register is 4 ones. So I am serially providing the 4 ones after 4 clock cycle period, and then the output will see 4 ones coming out from the last flip-flop. So 4 1 1 1 1 outputs are available ready now, and then again now we can apply the flip-flop like a clock. Then this one ready to come out. This is what. So after 4 clocks cycle, the data which is available in this shift register, serial in, serial output, shift register outputs are all ones. This is what we expressed in the truth table. Initially we can take the 4 zeros and once clock applied, this down arrow which indicates the negative edge clock and up arrow indicates the positive edge clock. So I am giving data input 1. So after applying that one, it will pass to Q3 and the remaining will be zeros. Second clock, I am giving 1. Already we can have a Q3 is 1, that is fed to QD, D2. So that in the second clock that will pass to the Q, D2 flip flop. So we will get 1 1 0 0. Next I am giving provide 1 1 0, and again I am providing 1. We will get 4 ones in the shift register. So in this way shift register works. Similarly, if you shift left, the same thing happen. Whatever we have given at the first flip flop 0, FF0 flip flop input, and then which is connected to the output of FF0 is giving to the flip flop 1. The output of flip flop 1 is feedback to the flip flop 2 likewise. Next, serial in, serial out shift register waveform. Same first first mode of shift register waveform. If I can have 4 flip flops, in this 4 flip flop first negative edge flop D1 input is all 0 zeros initially. So the first clock negative edge, then this one is for example 1, remaining all are zeros. You will get output because we are providing D input at the first clock. The next clock, this DQ3 is 1 because we are constantly providing 1 1. At that time Q2, second flip flop, this is 1, this is Q2 is 1, this is 0 0, and third flip flop Q3 is 1, Q2 is 1, Q1 is 1, and Q0 is 1. And the fourth flip flop, fourth negative clock, We can providing again at the D input is 1, Q3 is 1, Q2 is 1, Q1 is 1, Q0 is also 1, so that we will get 4 ones in the output. So that after four clock cycles, we can have 4 ones. Next case is serial in under parallel output shift register, serial in parallel out SIPO. In this case, data is given in serial and collect the data in parallel. The data is loaded bit by bit. The outputs are disabled as long as the data is loading. And once the data is loaded, then it is ready to collect the data in parallel way. Four clock cycles are required to load a 4-bit word as we have seen in the first case. So serially we have loaded. So it is serial in parallel. So to load all the for example 4-bit shift register, to load the 4 bits in the outputs of each flip-flop, it requires 4 clocks. Hence the speed of operation of SIPO mode is same as that of SISO mode. In that SIPO, the input of the second flip-flop is the output of the first flip-flop and so on. And the thing is that we are providing the serial data input, and the output of first flip-flop is fed to second input, and second output is fed to third, like this one. Next, this output is fed back to the fourth flip-flop. We can call it as anyway. I am taking in this case FF1, FF2, FF3, FF4, and collecting the output parallelly and taking the output parallel. This parallel output. So of course the output is fed to next following flip-flop, but I take the output parallel. And clock is giving, in this case also the clock is giving synchronously to all the flip-flops, and also I am providing clear if we want to initially provide the zeros in the all flip-flops, so that by providing clear input we can reset of all flip-flops into zeros. The same clock is applied to each flip-flop since the flip-flops synchronize each other. The parallel outputs are used for communication. And parallel in serial out shift register, in this case input is we are providing parallelly and collecting the data in serial mode. The data entered in a parallel way, the output comes in a serial. Output of previous flip-flop is connected to the input of next flip-flop because we need to collect the serial. So of course we are providing the input to the input of each flip-flop is parallelly, but collecting the data in serially. So it must be connected that one flip-flop output is connected to the input of other flip-flop. But one interesting point is that the output of previous flip-flop is connected to the input of the next flip-flop via combinational circuit to get this parallel in under serial output. The binary input word B0, B1, B2, B3 is applied to the same combinational circuit. There are 2 modes in which this circuit can work, namely shift mode or load mode. So the 2 actions happen in this parallel in serial out. First, initially loading of data into parallel of the inputs, and then in some other mode we can collect the data in serially. So in order to get this, also it is required, we need to figure it out when the mode, when it is shift mode or when it is loaded mode. Block diagram of parallel serial out register. In this diagram we can see 4 T flip-flops connected with the clock, and then the output of first flip-flop. The output of first flip-flop is connected connected through some combinational network, and then that output is connected to input of second flip-flop. And this output of second flip-flop is connected to combinational circuit, and output is fed back to the third input. Likewise, we can connect a parallel input and a serial output. So at final flip-flop, we can connect the serial data. What about the parallel input? So all the B0, B1, B2, B3, B0, B1, B2, B3 inputs are fed to these combination circuits, and the initial value is like first B0 is directly connected to the D0, and B1 and B2 and B3 are connected through some combination circuits. We can have some external like control circuit, control input, which is nothing but shift load bar, which will like when we are given 0, which will work as a load. When we are given 1, logic 1, then it will work as a shift mode. So our main aim is that we are providing like parallel input, and then how can we work like serial output. Load mode, when shift by load bar line is set to 0, the second, fourth, sixth like an even number of AND gates are active, hence the bits B0, B1, B2, B3 are passed to the corresponding flip-flop. If you connect this one is 0. When it is 0, this 0 passing through the inverter will get 1. That 1 is connected to 2, 4, 6. These are when AND gates are one input is 1, then which means that which allows the bit data B0, B1, B2, B3 is allows, which this 2, 4, 6 AND gates are allows to the second input, that second whatever the second input is passing through the output of the gate. So this is already, if it is 0, because the 0 directly comes to this one. 1, 3, 5 AND gates are 0 means immediately the output is 0. What does it mean? The all odd AND gates are providing 0 means it is even AND gates are providing the data, parallel data. The data is passing through the OR gate and available in the D0, D1, D2, D3. Once the clock is applied, each time whatever the data available loaded during the shift by load bar is equal to 0, the data is available, then we can move this next mode, like shifting mode. In the shifting mode, the second, fourth, sixth gates are inactive. All even number of gates are inactive and all odd number of gates are active. When odd number of gates are active, we are not able to load the data, but we can shift the data. At this time, the first, third, fourth gates will be active, and then shifting of the data will be left to the right. In this mode, the fourth bit binary input B0, B1, B2, B3 is applied to the data inputs D0, D1, D2, D3 respectively of the 4 flip-flops. As soon as the negative clock edge is applied, the input bits will be loaded into the flip-flop simultaneously in this parallel input and parallel output. So directly we can, the clock is applied, then the input bits are available and loaded into the flip-flop simultaneously. The loaded bits will appear simultaneously to the output side. Only clock pulse is essential to load all the bits. Block diagram for the parallel out register. This is the diagram which consists of 4 D flip-flops, and clock is same clock connected to all flip-flops synchronously. And then the data I am providing parallelly to all flip-flops. I am not connecting one flip-flop output is connected to the other flip-flop. I am connecting the data parallelly to all individual flip-flops. B3 connected to D3, B2 connected to D2, B1 connected to D1, B0 is directly connected to D0. And at the same time, and pick up the output. Pick output for the Q3, Q2, Q1. If I'm not connect, pick up that output parallelly, maybe we would have not get that the output parallelly. So when we are providing in data inputs parallelly and collecting, extending that Q3, Q2, Q1, Q0 parallel, then we can collect the data the same time by applying the clock. Then we move to bidirectional shift register. The binary number, after shift each bit of the number to the left by one position, will be equivalent to the number produced by the multiplying the original number by 2. If I am providing 1010, this is binary number which is equivalent in decimal number is 10. This binary number, after shifting each bit of number to the left, for example left shift, in this left shift the resultant data will be equivalent nothing but multiplying that the binary number after shifting each bit of the number to the left by one position will be equivalent to the number produced by multiplying the original number by 2. We can take 10 is nothing but 20. So left shift, if you take this left shift 0, 1, 0, 1, right shift 1, 0, 1, 0, not 1. Take this one. I am taking just simple number 0, 0, 1, 0, which is equal to 2 in decimal. If I am shifting this number to the left, if I am shifting this number to the left 0, this one is moved to that one, this one moved to this place, replace with this last one is 0, which is equivalent to 2 into 2. That is what it says. If it is right shift, if it is right shift 0, 0, 1, 0, shifted to right, this one is moved to last, this last one is come out, and this one is come to third place, this one is come to this one is come to first place, next 0, next 0, and last one is filled with 0. So which is equal to 2 by 2, which is nothing but 1. So right shift, which is simply in decimal number equivalent to divided by that given number, left shift nothing but multiplied by that number 2. So to perform the multiplication and division operation using shift register, it is required that the data should be moved in both direction. So in order to achieve this both direction, like bidirectional, such left or right shift in the register, such registers are called bidirectional shift register. Even we can provide this multiplication and division by 2 circuit, then we can achieve this bidirectional shift register. The block diagram for bidirectional shift register, and in this diagram we can have 4 flip-flops, clock and clear as usual, and then we can have DR input, DL input. If we are providing a right shift, the input is fed at the first NAND gate, and if we are providing left shift, we are providing the DL input at the 8th gate. And the shift load or M input, M is the mode select input, like in which like in load mode or shift mode. Shift right operation, if M is equal to 1. When M is equal to 1, directly it is connected to odd number of gates. When odd number of gates, whatever the data it is available, that is shifted to right. The right shift operation M is equal to 1. Odd number of gates will be enabled, but the even number of gates will be disabled. The data present on the data input DR is shifted bit by bit from the 4th flip-flop to the 1st flip-flop when the clock is applied. Shift left operation M is equal to 0. M is equal to 0. When M is equal to 0, this M is 0, M bar is equal to 1. When M bar is equal to 1, 2, 4, 6, all even number gates are 1, logic 1. It does mean whatever the data available in the second input of one gates, that will be come to this output and then available at the D flip-flop. Whenever clock is applied, the data shifted to the left. If you take one case, if I am considering one case, M is equal to 0 means M bar is equal to 1. All even number 1, 1, 1, 1. Now I am providing the data DL, for example 1101. This data is available, like the first clock it is available 1. So what does it mean? This is about second even odd number of gates, nothing but zeros. All odd number of gates zeros. So 0 is available in the odd number of gates and the gates. So the data is available 1 and 1. This 1 is here. That 1 come out from the OR gate is 1 is here. So in this time, so at the time clock, so 1 is ready in the clock. So that one passing through the Q1. That one is available in the next AND gate of the second input AND gate of D6 gate. So in the next clock cycle, this one, the data is available in this one shifted to D1. Like this is comes under this one is available 1. So in the second clock, first one, second clock, the D0 is high. First clock D1 is high. Second clock both the D0 and D0 and D1 is high. Remaining all are zeros. So in this case, in this way, we can shift that data. We can shift this 1101 data after 4 clock cycle. The data is, this is third, first, second, third, fourth. In the 4th clock cycle, 1101, 01. This data is available. 1101 data is available in this shift register. In the M is equal to 0. Next, universal shift register. A register where the data is shifted in one direction is known as unidirectional shift register. And in both direction, if it is shifted bidirectional. In the universal shift register is a special type of register which can load the data in parallel way and shift the data in both directions, left and shift right. The design of 4-bit universal shift register using multiplexing and flip-flops are shown in the figure. This is the diagram. In this diagram, we can provide with 4 multiplexers, like each multiplexer provided with the 2 select lines S0, S1. These S0, S1 select the which input is selected, and then we can have 4 D flip-flop. This is the truth table. When 0, 0 inputs, no change. When 0, 1, shift right of this universal shift register. 1, 0 of the select lines. Sorry. 1, 0 means S1 is 1, S0 is 0. It is like a shift left. If providing 1, 1, it is like a parallel loading. If I am providing 1, 1, one case I am taking, S0 is equal to 1, S1 is equal to 1. What does it mean? That means third input, 0, 1, 2, 3 are the 4 inputs. 0 is the first input, 1 is the second input, the second is the third, like that. 0, 1, 2, 3, when S0, S1, 1, 1 means third input is enabled. Third input, all third inputs are enabled. When third inputs are enabled, M4 is directly available here, M3 directly available here, M2 directly, M1 directly available here. This will pass to the output in the muxer when S1, S0 is 1, 1. So the data is available directly here. That data, for example, all 1, 1 ones. This data, when clock is applied, immediately the data will be collecting at the output. If you take one case for shifting, 1, 0, shift left, 1, 0, shift left. S1 is 1, S0 is 0. What does it mean? Second, two second input, this 2 input. This number 2 means from LSB to third input, LSB bit. So this path is enabled now. What path is means? So in this case, shift left, it will happen shift left. So first we will see here, serial input is given to first this input, this flip-flop. Let us consider this flip-flop, this muxer is muxer, like this muxer, 0 muxer, 1 muxer, 2 muxer, 3 muxer. 0 muxer, second input is enabled and passing through the data, and this data available here, D. In that clock, the output will get output. That output passing to the first muxer. The data is available in the second clock and passing through that clock value, and then the second clock you will get second input, first and second inputs, and that will be connected to this second of the second muxer. That will be data available in third clock and passing through the data D, and you will get some output. And then after fourth clock, the data is available in the fourth clock, negative edge clock. The data is passed to the muxer. This one is passing to the D, and you will get that output. That data is available in the each flip-flop. So for example, I am sending all ones here. After 4 clock cycle, it will be shifted and available data in 4 ones. Likewise, it is shifted left. So in this way, we can shift the left. We are providing 0, 1. S1 is equal to 0. S0 is equal to 1. It will be shifted right. In this way, we can have shift registers. When we come to applications of the shift register, basically parallel to serial converter, also the shift register used in serial to parallel conversion, and also sequence generator, and the best application is that counters. The shift register, which is used as a parallel to serial converter, which converts parallel data into serial. We can see this kind of application in analog to digital converter ADC, when the data is giving to the parallel, and then we will serially communicated, like passing through the cables or wireless. We can send the data in serial. So at the time of transmitter, it will be available. And then serial to parallel converter, we can see that the receiver, we can get all the serial data coming from the channel, and then converted to giving to serial to parallel converter shift register. Then it will convert serial to parallel, and it will be again get back that your original analog signal from that parallel binary information, so which is available at the digital to analog converter. Shift register along with some additional gates generate the sequence of zeros and ones. Hence, we can use this shift registers as a sequence generator. And also, shift registers used as counters. There are two types of counters based on the type of output. From the rightmost D flip-flop is back connected back to the serial input. So those names like ring counter or Johnson counters. So in this way, we can use in a parallel to serial and serial to parallel converter, sequence generator, counters especially. So this kind of this kind of application it is possible by shift registers. So we can study the shift register by considering all these things. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.